Okay, imagine this for a second. What if an AI could read an entire novel, or maybe a company's entire legal history, or even your entire medical history and remember every single tiny detail perfectly? Well, today we're going to dive into a brand new architecture that's trying to do exactly that.
It's a really strange paradox, isn't it? I mean, we've got these incredibly powerful AI models. They can write poetry, they can write code, but if you ask them to remember one specific detail from the beginning of a really long chat, they just can't. And this isn't some small bug, it's a fundamental, deep-seated limitation that researchers have been banging their heads against for years. All right, so let's get into the weeds here. The heart of the problem is something we call the AI memory bottleneck. Basically, right now, if you're building an AI, you're stuck with this awful choice. You can either have a model that remembers things with perfect, crystal clear accuracy, but only for a little while. Or you can have a model that can handle huge amounts of text, but it has to compress all that information, and when it does that, well, it's bound to lose some really important details along the way.
And this really breaks down the two main ways we've tried to solve this. On one side, you've got transformers. These are the engines behind models like GPT, and they're amazing in understanding context. Why? Because they literally look at every single word and how it relates to every other word. But that power comes with a crazy price tag. The cost? It's quadratic. That means if you double the text length, the cost doesn't just double, it quadruples. It gets exponentially slower and more expensive. Then on the other side, you have linear recurrent models. These guys are super efficient, they can chew through massive sequences, but they do it by constantly squishing the past into a tiny, fixed-size memory. It's like trying to stuff an entire library's worth of books into a single backpack. You're gonna lose stuff, important stuff.
So, the big question is, how do you get out of this trap? How do you break this trade-off? Well, the researchers behind this new work looked for inspiration in the best learning machine on the planet, our own brains. Think about it. Our brain isn't just one big memory drive. It's this incredible interconnected network of systems, right? You've got short-term memory, long-term memory, working memory, all talking to each other. And that was the key. And I love that the researchers actually put this quote in their paper. It perfectly nails the philosophy here. Memory isn't just this passive thing, like a hard drive storing files. No, it's an active process. It's all about the art of paying attention, figuring out what's important enough to remember. And that idea leads us straight to the core concept of this new model.
And that core concept is called surprise-based learning. Just think about your own life for a second. What do you remember most vividly? It's probably not the boring, everyday stuff. It's the unexpected moments, right? The things that broke the pattern. Well, this AI works on the exact same principle. It's constantly making predictions, and when a new piece of information comes in that completely shatters those predictions, that's surprise. The bigger the surprise, the more important that piece of information must be, and bam, it gets stored away in long-term memory. It's just a really elegant and intuitive way to figure out what actually matters.
So, that finally brings us to the star of the show, Titans. And let's be clear, this isn't just some minor tweak on an old model. No, this is a whole new family of architectures, built from the ground up with one goal in mind, to give AI a powerful, long-term memory that works a lot more like our own.
Okay, so let's pop the hood and see how this thing actually works. You can think of it as having three main parts, all working together. First, there's the core. This is basically its working memory, its short-term attention, dealing with what's happening right now. Then you have the persistent memory. This is like its built-in knowledge base, stuff that doesn't change, like the rules of grammar. But the real magic, the absolute game changer, is that middle part, the neural memory. This is its long-term storage. And here's the crazy part. It keeps learning and updating itself while it's working. As it encounters new, surprising stuff, it writes it to memory on the fly.
So how does that on-the-fly learning actually happen? Well, it's a pretty elegant little three-step dance. Step 1, it measures surprise, just like we talked about. It sees how much new data rocks the boat. Step 2, it updates its memory. But it doesn't just jam the new info in there. It combines the momentary surprise with a history of past surprises, kind of like building momentum. And finally, step 3, and this is so important, it intelligently forgets. It has this adaptive mechanism that prunes out old, less relevant memories to make room for new, important ones. See, it's not just about remembering everything. It's about knowing what's worth keeping. And another really cool thing is that Titans isn't just one single model. It's more like a flexible framework, a whole family of architectures. For example, you have the Memory as a Context version, or MAC. This one pulls relevant memories from storage and just adds them to what it's currently looking at, giving it more context. But then you have the memory as a gate version, MAG, which is different. It uses its memories to control and filter the information that's flowing through the network. This kind of flexibility is huge because it means you can tailor the architecture for all sorts of different jobs.
Okay, so the theory sounds absolutely incredible, right? But does it actually work in practice? To figure that out, the researchers decided to put Titans through pretty much the ultimate memory test for an AI, the needle in a haystack challenge.
Now, the idea behind this test is super simple, but it is absolutely brutal. You take one tiny critical piece of information, that's your needle, and you bury it deep inside an enormous, overwhelming document full of distracting junk. That's your haystack. Then you ask the AI a question that is impossible to answer unless it can find that one specific needle. It is the ultimate test of paying attention and recalling something from way, way back.
And wow, the results are just staggering. Seriously, just look at this graph. On this benchmark, you can see other models, even huge ones like GPT-4. Their accuracy just tanks as the haystack gets bigger and bigger. But look at Titans, that red line just cruising along at the top. It maintains near-perfect accuracy. We're talking about sequences over 1 million tokens long. It's practically a flat line of success. This isn't just an improvement, this is a total game changer.
And this table tells the exact same story, but with the cold, hard numbers. Take a look at a model like Mamba 2. At a 4K context, its accuracy is already falling apart. By the time you get to 16K, it drops to 0. Nothing. It has completely lost the needle. Now look at Titans. 98%, 97%, 97%. That just doesn't forget. That level of consistency as the haystack gets bigger and bigger is what is so absolutely mind-blowing here.
So you gotta ask, what's the secret sauce? What makes its memory so incredibly good? Well, one of the key insights from the paper is that the memory module itself needs to be deep. It's not just about having a lot of memory, it's about having layers of memory. On this chart, performance is measured by perplexity, which is really just a fancy word for how confused the model is. Lower is better. And you can clearly see that adding more layers to that neural memory, it makes the model way less confused, way more confident. A deeper memory just lets it store more complex, abstract ideas about the past. All right, so this all brings us to the really exciting part, the big so what? What does a future with this kind of technology actually look like? What happens when you basically remove the limits on an AI's memory?
Well, the potential applications are just transformative. Seriously, think about it. An AI that can read a company's entire legal history to find one specific precedent, or one that can process a patient's whole life of medical records, spotting subtle patterns a human doctor could easily miss. It could understand huge, complex code repositories to find bugs, or model an entire human genome to accelerate biological research. I mean, these are the kinds of problems that, until now, were basically impossible for AI.
And again, this is not just a small step forward. The paper makes a really powerful theoretical claim here. It says that for any task that involves keeping track of things over time, Titans are just fundamentally more expressive, more capable than transformers and most of the other modern models out there. This really is a foundational leap in what AI architecture is capable of. So I want to leave you with this question. We've always kind of assumed that AI creativity is held back by its short attention span. But what happens if an AI can hold, let's say, the entirety of human knowledge in its working memory with perfect recall? What kind of new connections is it going to make? What completely new ideas will it come up with? That's a future that, thanks to work like this, suddenly feels a whole lot closer.